Hello, I'm Doug Sicker. I'm the co-director of the IRLE, and today we're going to talk a bit about some electricity fundamentals. And this isn't going to be a technically deep talk. The idea here is just to give you some familiarity with some concepts. So to start, I'm going to share my screen. Hopefully this will be captured. When we talk about fundamentals of electricity, there's a logical starting point, which is the concept of current. And current is nothing more than the measure of the flow of charge. And we can think of this as being analogous to the flow of water. So just as water flows down a stream or through a pipe, the same kind of concept applies when we think about electric current. And what's flowing here are electrons. So we can measure the flow of electrons by this concept called an amp. And that's represented by the symbol I. And all it means by an amp is 1 amp is the flow of a large amount of electrons, like 6 to the 18th, that flows across a point over 1 second. So it's a large quantity of electrons. It's a fairly small amount of charge, 1 amp. And we should think of this again as this analogy as the electrons are flowing just as water flows. The next concept to talk about is that of resistance. And this is simply the opposition to that flow of that current, or the opposition to that flow of electrons. This is really just a restriction, just as a hose might be restricted. The same kind of concept applies in electricity. And here we use the term ohms and the letter R to represent resistance. The next important concept is the idea of voltage. And voltage is nothing more than the electric potential, or we could think of it as the pressure, just like water pressure. And if we again go back to the hose analogy, if we have a hose with a nozzle on the end, and we can think of that nozzle as the resistance, and maybe the nozzle is cranked down a little bit, and we can think of the voltage as how much water we've turned on, that pressure, that force at the spigot. As we turn up that voltage, what's going to happen is the resistance is going to stay the same, but what will go up will be, as it turns out, the current. So as we apply more voltage, we'll see a higher current if we keep the resistance the same. This is represented by a pretty simple, very simple concept, which is the voltage is equal to the current times the resistance. You can, of course, move this around. We could talk about the current being equal to the voltage divided by the resistance. And that's a really good way of thinking about it. And if we think about what I just described, where the resistance stays the same, if we increase the voltage in that situation, of course, the current's going to increase as well. Now, when we talking in the power grid, the common concept again is power. And how we get power is simply taking voltage, that pressure, times the current or the flow. So this is really, as we start thinking about a rate and a rate of work. So again, the pressure times the current gives us that power, and power is measured in watts. And that's an instantaneous concept. Power is what you get when you take a certain flow times a certain pressure. And what we get out of that is the ability to do work. What we think of in terms of watts is often what we judge as a light bulb or any other kind of device. You know, what's the power required for that to operate? We'll come back to that in just a moment. A concept that's commonly confused with power is the idea of energy. And energy and power are different. Energy is what we consume across time. It's power across time. It's not the rate. It's this concept of a watt hour. So energy is something that happens. We consume energy over periods of time. Often we think of that as kilowatts. That's more commonly than watt hours. We think of kilowatt hours, and we see this on different on bills that we pay, as well as on meters on the side of our homes. So to dig in a little bit deeper, as you see on this figure on the right, the measurement on this older meter is in kilowatt hours. And you can look at that across those dials and be able to determine the amount of energy that's been consumed. So again, power is this measure in watts, and that's voltage times current that's happening at an instance. When we take that power across time, we get what we think of as energy. And as I said before, it's not so common to think of watt hours, which is 1 watt for an hour, the consumption of 1 watt for a period of an hour. We tend to think of things as in kilowatt hours. Not surprisingly, that just means 1,000 watt hours. To give you a little better reference for what that might mean, if I had 10 100-watt light bulbs running for an hour, that's a lot. Again, 100-watt light bulbs, a powerful light bulb, and 10 of those running for an hour, I would consume 1 kilowatt hour. Again, it's that concept of power across time. I would encourage you all to dig in a little more deeply. Go to this website, and what I have here up right now is the Central AC energy calculator. It's a fun little tool to play around with to see the impact of different devices in a home, such as a refrigerator or, again, an air conditioner. Another thing that's neat to look at is the difference of a 100-watt light bulb or a 60-watt light bulb compared to, say, a 10-watt LED, which again can have the same equivalent output in terms of lumens, but at a fraction. Again, the LED is a fraction of the energy over time. It's the power over time that needs to be consumed. So I would encourage you to take a look at that. Again, do review these concepts. We'll be talking about them when we meet in person. Thank you for your time.